Silicon and germanium acts as pure semiconductors. So, in practical cases, most widely used semiconductors are these two materials, silicon and germanium. And from these two, most widely used semiconductor is silicon. Germanium is used for special application purpose. Only in special semiconductor devices, the germanium is used. For the purpose internally, it has some reasons. Okay, now I will explain those reasons. Germanium atomic number is 32. Silicon atom number is 14. So valency orbit of silicon is third orbit, and the valency orbit of germanium is the fourth orbit. So the valency orbit is very far from the nucleus. In germanium, the valency orbit is very far from the nucleus. So the leakage current is very high in germanium semiconductor. This is one of the important points. So in germanium, the leakage current is intense of microamps. For silicon semiconductor, the leakage current is defined in terms of nanoamps. Nano is 10 to the power of -9 and micro explains 10 to the power of -6. So leakage current is more in germanium compared to the silicon. So that I naught of germanium is more compared to the silicon. So I naught of silicon. Okay, this is one of the reason, right? And similarly, we have discussed some other reasons here. And silicon availability is more compared to the germanium. This is also one of the reasons. Silicon can operate at higher temperature ranges. Silicon can operate at higher temperature ranges than the germanium. Compared to the germanium, it can be operated at higher temperatures. So here we can write like the silicon has high temperature stability. So this is one of the reason for most widely used. Silicon temperature stability is very high, and the availability of the silicon is also very high. And in CMOS design, in CMOS technology, silicon dioxide layer acts as a super insulator compared to the germanium dioxide. Silicon dioxide SiO2 acts as super insulator. Silicon dioxide acts as super insulator. So this concept, this analysis is used in CMOS technology. CMOS technology. In CMOS design process, silicon dioxide layer is used because their insulators are required. So that purpose, this layer is used here. Silicon dioxide acts as a super insulator. And another advantage of silicon is doping process is easy, right? Doping process is easy in the silicon compared to the germanium. Doping process is easy in silicon than the germanium. So now what is doping? Doping is nothing but adding impurity to pure semiconductor. Adding impurity to pure semiconductor is called doping. So this process is easy in silicon material compared to the germanium. So from all these reasons, we can write one simple point here. Silicon is the most widely used semiconductor compared to germanium. And here I want to explain again another simple concept here. So mobility concept, mobility which is denoted as mu, right? Mobility explains the probability of movement of the electrons. The probability of movement of electrons, right? So that purpose here I am taking one basic material. Let us say this is one of the material, right? Or we can call it as a conductor. So this conductor is excited by the one DC power supply. External biasing I am taking now. The external biasing is a V volts. So whenever some external power supply, external DC voltage is connected to this conductor or this material, then the carriers are moved from one side to another side. If you assume this is a semiconductor, then the carriers are moved from higher potential to lower potential. So the carriers moves towards this side. Let us assume like this. The direction should be in this direction. And again I am taking now the length of the semiconductor, the length of this material is a L now. Just I am assuming as a capital L. So whenever some voltage is connected to the one conductor or one material with length L, then internally it induces the electric field intensity, denoted as capital E. So we can write this capital E is equal to voltage by length. So the voltage applied here V and the length of the material is L. So units are, we can write volt for meter. This is electric field intensity, right? And due to this electric field intensity, the charge carriers are moved from one side to another side. That means these charge carriers has velocity. Velocity is nothing but speed in particular direction. So the charge carriers are moved from higher potential to lower potential with some velocity. So the velocity of the charge carriers is directly proportional to electric field intensity, right? So from this here I am writing like this here, this is I am writing as like this. So this is nothing but velocity of the charge carrier. Velocity of the charge carriers. What are the units? Meters per second. So velocity of the charge carriers is directly proportional to electric field intensity. If the electric field intensity is increases, velocity of the charge carriers also increases. The movement of the charge carriers also increases. If the electric field intensity is decreases, then the velocity of the charge carriers is decreases. So both are directly proportional. So from this I am writing one standard equation now. Velocity of the charge carrier. Velocity of the charge carrier is equal to mu E. Here mu is also called as proportionality constant or mobility, because due to that electric field intensity, the charge carriers are moved from one side to another side. The probability of movement of the charge carrier is explained by one parameter. That parameter is the mobility here. So this is one of the standard equation used in electrostatic field. That equation is velocity of the charge carrier is equal to mu into E, or we can write V is equal to mu into E. Here E is the electric field intensity and V is velocity of the charge carriers. Then I want to find the units of the mobility from this equation. So for that purpose, from this equation I am writing mu equation now like this. Mu is equal to velocity by electric field intensity. The units of the velocity is meters per second, and electric field intensity units are volts per meter. Volts per meter. Then if you write standard units, now it becomes a meter square per volt second, or we can write in terms of centimeter square per volt second. So these are the units of mobility. And one more point we can write here, mobility of electrons is always greater than the mobility of holes. Here mu p is nothing but mobility of holes, mu n is nothing but mobility of electrons. So mobility of electrons is always greater than the mobility of holes. This is also one of the important points. So please take this now.